Just a minute. 20. Max up. Some technical problem, 1 minute. Now listen everyone. For your periodic test, 2 chapters, that is a revision exam. First schedule, month of August, will cover electric charges and field, potential and capacitance. First 2 chapters, month of August. September, current, electricity and magnetic effects of electric current. So October, magnetism, electromagnetic induction and alternating current. 3 chapters. So Faraday's law of electromagnetic induction. So morning we discussed NOMA, that is the induced EMF with a stationary coil and a moving magnet. So this is experimental studies.
Faraday's law of electromagnetic induction. Electromagnetic induction. Magnetic induction. Electromagnetic induction. Electromagnetic induction is the phenomenon by which induced EMF, or induced current, is produced in the coil, due to the change of magnetic flux produced in the coil. Faraday's experiments. Consider a solenoid, or a coil, at rest. Take a bar magnet, and move it towards the coil. Attach a galvanometer to the coil, as shown. When the bar magnet moves towards the coil, galvanometer deflects in one direction. When the bar magnet moves away from the coil, galvanometer deflects in the other direction. In the first case, the magnetic flux increases, whereas, in the second case, the magnetic flux decreases.
Toward the coil, magnetic flux is increasing. Away from the coil, magnetic flux is decreasing.
Same results may be obtained if the experiment is done keeping the magnet at rest and moving the solenoid towards the magnet.
Now stationary bar magnet, moving coil.
Even in this case, an induced EMF, or current, is produced in the coil. If both the bar magnet and the solenoid are at rest, we cannot produce any induced EMF, or current, in the coil. With this experiment, Faraday concluded that to produce an induced EMF, or current, in the coil, there should be some relative motion of the coil, or the magnet, or both. Both at rest cannot produce any induced EMF, since there will be no change in the magnetic flux of the coil. Magnetic flux. Definition: the number of magnetic induction lines passing through some area A of a coil is called magnetic flux. Explanation: a coil of area A is kept in the magnetic field B bar in such a way that the normal on makes an angle theta with the magnetic field B bar, and n cap is the unit vector perpendicular to the plane of the coil. The magnetic flux, phi, is equal to the dot product of the n cap and B vector. Therefore, phi is equal to A into n cap dot B vector. Phi is equal to A into mod n cap into mod B vector cos theta. Phi is equal to A into 1 into B cos theta, since mod n cap is the magnitude of unit vector, which is equal to 1 unit. Therefore, we get phi is equal to AB cos theta. Say equation 1. If n is the number of turns in the coil, then phi is equal to NAB cos theta. Say equation 2. Special cases. If theta is equal to 0 degrees, then phi is equal to NAB cos 0 degrees. Therefore, phi is equal to NAB, since cos 0 degrees is equal to 1. If theta is equal to 90 degrees, then phi is equal to NAB cos 90 degrees. Therefore, phi is equal to NAB into 0. Cos 90 degrees is equal to 0. Therefore, phi is equal to 0. SI unit of flux is Weber, or WB. The flux through the coil can be altered by changing the magnitude of magnetic field induction, B, the angle, theta, the area of the coil, A, the number of turns of the coil, N. Faraday's law of induction. Faraday's first law. The induced EMF produced in the coil is directly proportional to the rate of change of the magnetic flux produced in the coil. Epsilon is proportional to minus d phi by dt. Say equation 1. The negative sign is due to Lenz's law. If n is the number of turns in the coil, then epsilon proportional to minus n d phi by dt. Say equation 2. From equations 1 and 2, we get epsilon is proportional to minus n d phi by dt. Say equation 3. Since phi is equal to BA, epsilon is proportional to minus d by dt of NBA. Say equation 4. Remove proportionality by introducing constant in equation 4. We get epsilon is equal to minus k d by dt of NBA, where k is the constant of proportionality, equal to 1. Therefore, epsilon is equal to minus d by dt of NBA. Say equation 5. This equation is also called Newman's law.
Please note it. The E is equal to minus d by dt NBA, Newman's law. So we already completed Faraday's first law and the second law. Just to note it. That Newman's law means E is equal to minus d by dt NBA, because pi value BA. So N means number of turns. Please note it. Okay. Okay, listen now. So based on Faraday's experiment, we can conclude that the law of electromagnetic induction. There is a two laws. First one, Faraday's law of electromagnetic induction. Second one, Lenz law of electromagnetic induction. We'll discuss one by one. Just a minute. August first week onwards for your periodic test. Maybe it is a revision exam. Dharnidharan, tell me Dharnidharan. Periodic test 1 for all the subject now. They will start with the August first week. Now the schedule is going on. Maximum tomorrow we will get idea for all the chapters. The physics also material preparation, everything is over. Today's CBSE 12th result, no, so that only it is taking time. Okay. Now listen, the law of electromagnetic induction. So electromagnetic induction, EMI means electromagnetic induction. So there is a two laws. First one, Faraday's law. So what purpose we are using Faraday's law? What is the purpose? So induced EMF. Till now we are discussing about induced EMF. Okay. So finding the magnitude of induced EMF. Magnitude means only the value. Finding the magnitude of induced EMF. So one more question. So which law it is applicable for? Finding the magnitude of induced EMF. Faraday's law, Lenz law, another one Maxwell law, Gauss law. So correct answer, Faraday's law. Finding the magnitude of electromagnetic induction, otherwise induced EMF. Magnitude. Okay. Second one, Lenz law. So what is the purpose we are using Lenz law means? It will give the direction of the induced EMF, whether it is in the anti-clockwise or clockwise. Finding the direction purpose, we are using Lenz law. So direction of induced EMF. Please note it now. For the Faraday's law of electromagnetic induction, the first law and the second law, it is the first law, changing magnetic flux produce induced EMF. Simple definition, changing magnetic flux produce induced EMF. First law. Second law, the rate of change of magnetic flux, it is equal to induced EMF. Otherwise, the magnitude of induced EMF is equal to rate of change of magnetic flux. Okay, in these two laws, using for finding the magnitude of induced EMF. That experimental studies, please note it for the Faraday's law. First one, induced EMF with stationary coil. induced EMF with a stationary coil and moving magnet. First one. Second one, this is experimental studies. First experiment. Second experiment, induced EMF with stationary magnet and moving coil. Induced EMF with a stationary magnet and moving coil. My voice is audible?
Yes, sir.
Okay. Third experiment, induced EMF by varying current in the neighboring coil. Induced EMF by varying current in the neighboring coil. Just a minute, somebody writing. Neighboring coil, current in the neighboring coil. Okay, so this is the three experimental studies. First one, second one, third one. So based on these three experiments only, we get idea from the Faraday's law of electromagnetic induction, the first law and the second law. Please note it. Okay. So next now, Lenz law. It is said by Lenz, 1833. So this is a general law for determination of the direction of induced EMF. Direction of induced EMF. So what purpose we are using Lenz law means? So finding the direction of induced EMF. Okay. Listen. This is one coil. It is connected with the galvanometer. So this is the current flowing direction. Now I will take one bar magnet. So this is north pole, this is south pole. Okay, moving with velocity v. So north pole of bar magnet is moved toward the coil. This is coil. The induced current, the flow in the anti-clockwise direction. Induced EMF, what is the direction? It is in the anti-clockwise direction. Is then north pole moving towards coil. Now the induced EMF, that is induced current, so induced current anti-clockwise direction. Okay. See the arrow mark one. This is in the anti-clockwise direction. Maybe diagram based question also there. So they will give only diagram. So based on the diagram which is represent, yeah, north pole, it is moving towards moving towards the coil. Then current direction, it is in the anti-clockwise. First condition. So now in this coil it is there now. In this coil nearby in this point, just a minute. So nearby coil, the polarity is not outside, but in this area the polarity is south. So nearby it is north, away from it is south. The polarity of coil. So polarity means north pole and south pole. This is the first case. Please note it, ma. We go for second one. Listen. That induced EMF, it is depends upon the motion of the bar magnet. Okay, now second condition. This is galvanometer. This is one coil. So now I will take one bar magnet. This is north pole. This is south pole. Coil moving away from the coil. Sorry. Bar magnet moving away from the coil. Refer the arrow mark, it is away from the coil. So north pole away from the coil. So away from the coil means the induced current direction is current direction. It is clockwise. So now toward the coil it is the polarity of south, opposite it is the north. In this side polarity is south, opposite side the polarity is north. Away from means. So only it is clockwise. So based on in this phenomena you can understand for the away from north pole the stationary coil. So it will generate the north and south attractive nature. So attractive nature means induced EMF clockwise. North and north, it is the repulsive nature. So repulsive nature means the induced EMF, it is in anti-clockwise direction. Please note it. Okay. So using Lenz law, we can find the direction of induced current. Using Faraday's law, we can find the magnitude of induced EMF. Magnitude means values. Direction means whether it is a clockwise or anti-clockwise. Induced EMF current clockwise or anti-clockwise. Okay. So up to that, today class I will wind up. Thank you so much. If you have any doubt, you can ask. Thank you.